All right, I think it's time. Welcome back to everybody. I hope you had a nice little break. I had a nice little break. There is no homework for tonight. We only had one day last week, so I figured we'd just roll it into the next one. I hope that's okay with everybody. I have big announcements. I've been thinking over the past little while, and I think my experience looking at the grades for the latest exam have confirmed to me my thoughts that maybe I should change some of the grading rules for the tests. So I'm changing some of the grading rules for the tests. Like I said, this is the first time I've done this kind of grading for this class, and I feel like it was more or less going okay, but there are some people at this point who have had bad luck on the tests so far and are sort of in a deep, inescapable pit because the unanswered questions continue to accumulate, and it's like you're going to have to do 30 questions on the last test, which is kind of unreasonable given the time frame that we have. And I didn't intend for that. Like, the whole purpose of this somewhat weird grading strategy was to alleviate the pressure on the individual tests because you're allowed to do it again, you know. So anyway, I have some changes that I think will help out a little bit for folks in that situation. If you've been, not everybody is in that situation, and some of you are doing great, and you will continue to thrive under the new rules. But anyway, what I have here is a new version of the checklist. So one change you will see immediately is there shall be, from now on, some partial credit. So the checklist now, instead of just having an empty box for each item, now has 3 boxes. So you can get either 1, 2, or 3 points on each question. So if you have already gotten items checked off on your list, those will automatically transfer as 3 points, the maximum credit. If you have missing ones, they will transfer as 0 points. I just because I don't want to deal with it, I'm not going to go back and regrade the previous tests. So if you have your old checklist, you should be able to just check off, 3 points for each of the ones that you already got. And then going forward on the test, you will get 0, 1, 2, or 3 points per question. And since we have 2 more exams, if you say on our next test you only get 1 point on something, you can try to do that one again on the final, and maybe you'll do better. If you do worse, I won't take the points away, so you can try to incrementally improve from one to the next if you want to do that. One other technicality, I don't know if anybody cares, but I removed the old number 24. So number 23 is curve sketching for polynomials. I had a more complicated curve sketching one also, but I decided let's cut that out just for the sake of time. If we have like an extra day at the end, maybe we'll add that back in, but let's just say we're going to skip that. And so I shifted the rest of them forward by 1 number, so the numbering is slightly different on the ones at the end. All right. Any questions about that so far? All right, and there are more changes which you can find on the back. So if it says, the first one there, any check marks obtained from earlier in the semester get 3 points for that item. That's what I said. Going forward, partial credit may be given for wrong answers. Every topic is now worth 3 points. And so your final grade will just be, I'll just add these up as if every topic will be worth the same amount of points, even though some are easier and some are harder, but the harder ones are worth the same as the easy ones. There's enough of them so that it'll even out. All right, points may be earned on our 2 remaining exams, which, just to remind you, March 26th, which is the last day of regular class, and then May 7th, which is the final exam. The final exam is 3 hours long, so you will have sort of a lot of extra time to finish up. The one on the last day of class is just 1 class done. And then, more big changes. Points may also be earned by appointment in the professor's office. Students may attempt 2 questions per week until the final exam. So this means if you are finding yourself in a hole right now where you have like 25 unanswered questions, you can come by my office and do the questions then, rather than waiting until the next test, all right? So here are the rules for that. You can attempt 2 questions per week until the final exam. I believe there's 4 weeks left until the final exam, maybe 5, depending on how you count them. I don't know. Including, you can come and do this tomorrow if you want to. So you can, if you feel like you're way behind in getting your things checked off, do 2 each week, and then by the time we get to the final exam, you'll have them worked out. All right, it says you may attempt ones which have not yet appeared on any regular exam. If you really want to, like we just did the curve sketching thing, it hasn't been on the test yet, but if you want to do that one early, you can do that. Tell me ahead of time which questions you want, and I will create the questions just for you. So don't just show up to my office and say, okay, I want to like take a little test right now. Tell me ahead of time so I can write the questions. And then the last one there, no reviewing or help from the professor on that same day. This is to avoid, what I don't want to happen is you come down to my office and you say, hey, can we just do like 5 examples of that? And then you take your little test and you've just sort of like memorized how to do it for 10 minutes and then you immediately forget how to do it after that. So to avoid that, I'm happy to go over, do examples or whatever, but not on the same day that you are actually doing your questions for credit. All right, and then here's just a little, this is my general availability times, although you will need to check with me and make sure I'll be around. Anybody have any questions about that? I hope that this seems appropriate and helpful to people who are feeling way behind. Yes?
So if you did one that was like before it appeared on a test, that means you could like earn the points before the test and then not have to take it on, like, let's say, the final.
That's right. Yeah. Yeah, in theory, if you wanted to, you could like pre-do all the ones that are on the final if you really want to, although I would rather not do that, but it's up to you. Yeah. Any other questions? Yes?
When will the answer key for exam 2?
Oh, I did it. I just didn't post it yet, so I'll do that later today. Yep. Sorry about that. Okay, great. Please let me know if you do have more questions about that, and let me know when you want to come by and do your 2 questions per week. Okay, let's get back to it then. So, on the list today, so we talked about number 23 last time, curve sketching for polynomials. And then let's do absolute extrema. That won't take all the time today. And that's actually the last topic, which is about the derivative. And then for the rest of the semester, we're going to be talking about the antiderivative, which is, it's kind of related to the derivative, but it's something, a new, fresh start, if you like. But anyway, one last time about the derivative. Let's talk about absolute extrema. All right, absolute extrema. We have talked already about relative extrema. This is a related concept, but this is called absolute instead of relative. So here's a kind of an example of what this is all about. What's the difference between absolute and relative? Something like, I don't like that. How about this? I don't like that either, sorry. I didn't draw this picture on my notes. How about that? All right, this is an example of a function which has several relative extrema. Remember, the relative extrema would be these points which are either bigger than or smaller than all the nearby points. So this one here, this is a relative maximum because it is bigger than all the nearby points. And the word relative refers to the fact that I'm talking about only the nearby points. And this is a relative, my I have found, if I take the iPad out of my cute case, that it works better. I think it overheats or something. Anyway, this is a relative minimum. Look at that. And then this over here is a relative maximum. All right. So these are the relative extrema. What are the absolute extrema? In every function, there are only two, if that. There could be less than two. But this one right here, this is the absolute extreme, absolute maximum. Absolute maximum. Absolute meaning it is actually bigger than everything else, not only the nearby points, but it is its y value is bigger than all other points. That's what absolute maximum means. The y value is bigger than all other points. All right. Whereas this one over here, this is a relative maximum because it's bigger than the nearby y values, but it's not the absolute maximum because it's not bigger than this one way over here. All right, that's the difference between relative and absolute. And this function here, you could ask, is this the absolute minimum? I say no, it's not, because there are other points with y values that are further down, like over here. In fact, this function, I mean, your interpretation of these little arrows I put here should be that this just continues to go down forever. And so actually this function has no absolute minimum. That's because there is no single point which is the lowest, because it keeps going down forever. All right, so this one here has no absolute minimum, since the y values go down forever. So there is no, in this example, there's no such thing as the one at the bottom, right? Because it goes down forever. Since the y values go down forever. All right? This is the idea between the idea of absolute minimum and absolute maximum. And I've said before, you know, the extrema are important in the real world. It's very important to tell when is the maximum of whatever. You know, if you're running a business, you want to know what is the maximum profit I can make or something like that. Or if you're driving a super fast race car or something, you want the maximum speed, whatever. The maximum and minimum are super important in all kinds of situations. Most of the time in the real world, what you care about is actually absolute maximum versus relative maximum. Like if you're trying to maximize your profits, if you're running a business, you really want the maximum possible. You don't want like the maximum of all the nearby profits, which would be like one of these. If your profits are here, it's better to put the profits up here. So in most of those applied settings, actually the absolute is what you're really looking for rather than the relative. All right? And this sort of strange good news, I suppose. Finding the absolute maximum and minimum is actually a little easier than finding the relative. You'll see why. Remember, we had two methods for finding the relative extrema. There were the first derivative test and the second derivative test, which both involve making some kind of increasing, decreasing chart, or that's the first derivative test. The second derivative involves the second derivative. They're a little confusing. But anyway, like I said before, sometimes there's always just sort of one absolute maximum, the one which is higher than everything else, and the one which is lower than everything else. But sometimes the max and the minimum don't exist. Like in this case, there's no absolute minimum. But we can make them exist. So these, I will say, there will always be an absolute maximum and minimum if we only consider a closed interval. See, the problem, like that one that I just drew, the reason there's no minimum is because the function is going down forever. But if you don't look at the entire real numbers, I mean, you only look at a specific interval of numbers, Here's a simple example. Let's just look at, say, y equals x squared. It's a nice looking parabola like this. Now, overall here, this does not have an absolute maximum because it goes up forever. It does have an absolute minimum right in the middle there. But if I restrict my attention only to a closed interval, let's say I'm only looking right here, then the function values that I'm looking at would be like from here to here. And in that little piece of it, there is a biggest and a smallest, right? So what I'm saying is, if you look overall the entire real line, then maybe it goes up forever or something, so there's no biggest. But if I only consider a closed interval, then you are guaranteed to have a biggest and a smallest. This is actually a theorem in calculus. This is called the extreme value theorem. It says if you have a continuous function and a closed interval, then it always has an absolute minimum and an absolute maximum. So in this little sort of simple example here, this up there, this is the absolute maximum, and this one down here would be the absolute minimum. All right? So if you want to be very specific about this, I could say something like for this function I'm trying to draw was f of x equal x squared. On the interval, let's say this is the interval 1 to 3. Right? What is the absolute minimum and the absolute maximum? It's easy if you're looking at the picture here. We can say the absolute minimum is at x equals 1. It's on the left side, right? It's this one over here. That's the minimum, the smallest one. And it has a y value of 1 squared, which is 1. Here the function is x squared. And so to get the y value, you would use x squared, but x is 1, so 1 squared is 1, right? And then the maximum, the absolute maximum is at x equals 3. That's over here, right? And what's the y value there? The y would be 3 squared, which is 9. All right? These are the absolute extrema of that function on that interval. All right. If I don't give you an interval, then you actually don't know if they even exist or not. And so a typical problem from this section on the homeworks or on the tests or whatever will always give you a function and an interval and say find the absolute maximum and the absolute minimum. If you don't get an interval, then actually you don't have enough information to say typically what the absolute extrema are. All right? Okay, great. What about, can I just say, so how about the same function, f of x equal x squared on, how about the interval 4 to 12? All right, what does that look like? Well, the picture would look similar. It's a parabola again, but this time the interval that I'm looking at is like way over here, right? From 4 to 12. But I think we can still, just because you know what this graph looks like, you can still say this is going to be the minimum point at the 4, and then the maximum will be over here at the 12, right? Because this parabola would continue upwards. So here, in this case, the absolute minimum is at x equals 4 and y equals 4 squared, which is 16. And the maximum, absolute maximum, is x equals 12 and y would equal 12 squared, which I guess is 144, right? These are easy just because we know what a parabola looks like. So it'll continue up. Since we're kind of on this side of the parabola, the 4 will be a smaller value and the 12 will be a bigger value when you look at the graph. All right. One more example, simply looking at the graph. How about f of x equals x squared again on the interval, let's try -1 to 3. So I'll draw the picture one last time. Nice and smooth. How about this? All right, -1 to 3. Okay, this actually, something slightly interesting will happen when you look at this one. -1 is here and 3 is here, right? So what about, and you know, the piece of the graph that I'm looking at is this portion of the parabola, right? What about the maximum and the minimum this time? The absolute maximum, well, you're looking at the biggest y value overall, which is on this end. It's at x equals 3. The y would be 3 squared, which is 9. At x equals 3, y equals 9, right? And how about the absolute minimum? Here's where something, I suppose, very slightly tricky happens. The absolute minimum is not on the other end. Remember, the absolute minimum means the smallest y value that appears overall, and I think you will agree, it appears in the middle at 0, right? It's not at the other end of the interval. So this, what I'm trying to explain is that these absolute extrema, they do not always occur at the two ends of the interval. Sometimes they occur at intermediate points on the inside of the interval. So here, the absolute minimum at x equals 0, the y is also 0 at that point. All right? So how can you predict where the minimum and the maximum value are going to be? They might be on the ends, but they might be just some random other point on the inside. I would say this point right here on the inside is not entirely random. This actually is a very special point. This is a point where the derivative is 0. This is a what we might call a critical number, right? So the moral of this little story here is the absolute extrema, the minimum and the maximum, always occur at the critical numbers or the interval endpoints. All right, this is a little something to remember. The absolute extrema always occur either at the critical numbers or at the interval endpoints. All right? They could occur at the ends or they could occur at a critical number, which would be, like in this case, this one is also a relative minimum, and it is the absolute minimum too. All right? They do not always occur at the endpoints, though. That's what I'm saying. They also do not always occur at the critical number. Sometimes they do occur at the endpoint. Here's a little, would you mind a little fun diversion? You can amaze your friends with this fun fact. This is a true fact. Tell your friends at lunch. I learned this when a few years ago, I went hiking with my kids, and we went to the tallest mountain peak in Connecticut. This is a true story. It's not very tall. The tallest mountain peak in Connecticut. It's like in the northwest of the state. And I learned, I looked it up afterwards. I learned that the tallest mountain peak in Connecticut is not the highest point in Connecticut. Think about that. This is a little conundrum. Anybody have an idea about how this could possibly be true? And I will say, this is not a trick question. There's no funny business here. I'm not talking about like some tall building or like a tall tree or something like that. It is straight up a fact. The tallest point, the highest point in Connecticut is not the same as the tallest mountain peak in Connecticut. Anybody know how this could possibly be true? It is really true. I will draw you a side view of the state of Connecticut. Looks like this. Right here, this is the tallest point in Connecticut. I mean, the tallest, it's not the tallest point in Connecticut, it is the tallest mountain peak in Connecticut. How could that not be the tallest point in the state of Connecticut? It actually is related to what I said in the box here. When I say tallest point in Connecticut, that means the absolute maximum elevation in the state of Connecticut, right? This highest mountain peak on this picture, you could say this is one of the critical numbers. It is a place where the derivative is 0. The absolute tallest point in the state of Connecticut either occurs at the critical numbers or the end points. So this is the true picture of what Connecticut actually looks like. Here's the state line with New York. And here's Connecticut, right? It does something like this. Do you see now? This is the highest point in the state. It's on the state line, and it is not at a mountain peak. It's not at the top of a hill or anything. It's like you're going up to another higher point inside of New York. And it happens to be the highest point in Connecticut because that's where Connecticut ends. Tell your friends, all right? The moral of the story is sometimes the absolute maximum point occurs on the edge. It doesn't occur at some kind of hilltop, all right? I can tell some of you are fascinated by this true fact about our dear state. I think actually this is true of many states, like in the Midwest. You know, like the Rocky Mountains are so big that many of the states have sort of a gradual upslope as you go east to west, and this will be true of all of those states also. They don't have individual mountain peaks that are higher than the points on the border. All right, amaze your friends with this fun fact. Okay, anyway, what this means is if your job is to find this fact in the box here, the absolute extrema always occur at the critical numbers or the interval endpoints. We've seen already in the past, like a typical example where you have to find the critical numbers. Usually there's like 2 or 3 of them, right? You find them by setting the derivative equal to 0 and factoring, something like that. If it's your job to find the absolute minimum and maximum, there's only like 2 or 3 options, right? The critical numbers, there's just a few of them, and you can just check each one to see which one has the biggest y value and which one has the smallest y value. So if it's your job to find the absolute extrema, this is why I said this is actually easier than what we've been doing the past few weeks. To find the absolute extrema, we simply check the y values at every critical number, which usually there's only like 1 or 2 of them, right? So this is not hard. Check the y values at every critical number and at the interval endpoints, right? You also need to check those. Interval endpoints. And then you check those y values. One of them will be the smallest, one of them will be the biggest, and those are the absolute minimum and maximum. So you pick the biggest and the smallest, and that's it. All right, so we're going to do a few examples like that. These questions typically will take you less time to do than a relative extrema problem where you have to find the critical numbers and then also do some kind of chart or plug them into the second derivative. Those are more complicated. All right. Okay, let's just try a simple example here. How about f of x equals 3x squared minus 12x minus 1, and your job is to find the absolute extrema on the interval -1 to 3. Remember, you'll always get an interval in a question like this. If I don't tell you interval, then typically there are not absolute extrema because the function goes up forever or down forever or something like that. All right, so we begin by finding the critical numbers. This is something that everybody remembers, I hope. You take the derivative first and then set that equal to 0 and solve for x. So I go f prime of x, which is, in this case, 6x minus 12, right? Factor as much as you can. This is an easy example, so all you have to do is, all you can do really is factor out the 6 times x minus 2, right? And then I'm going to find the critical numbers by setting f prime equal to 0, which looks like 6 times x minus 2 equals 0. So you can divide by 6. It says x minus 2 equals 0, which means x equals 2 is the only critical number. All right. So really there's only, remember what I said, my strategy is find the critical numbers and then just check the y values at each one. And also check the interval endpoints. So I'm going to make a little sort of small chart here of y values So x and f of x. Remember, you know, the y value is given by the function f of x. And I need to check the x equals 2, because that's a critical number. And I also need to check the two interval endpoints, -1 and 3. So what goes in your chart is the critical numbers, of which there's only one in this example, and then also the endpoints. But anyway, you just check the y value for each of these 3 points. This is not hard to do, although in an example like this, you might want to use a calculator. As usual on our tests, I will make the function easy to plug into. Make sure that you don't plug into this one, the derivative. You are looking for the y values, which means you must use the original function straight up like it is, not the derivative, which would tell you the slopes, which we don't care about at this point. So here, I'm going to plug these in to the original function. Like if I do f of x, this one for 2 would be 3 times 2 squared minus 12 times 2 minus 1, which you could do this by hand if you had to, but put it in your calculator if you like. This is, sorry, I did this ahead of time. I just copied the wrong answer. -12 is what I got when I did this ahead of time. All right? So that's one of them. You do the same thing for the others, and I will just say plug into f of x, not f prime of x, right? In this case, there are many, I'm sure you know by now, there are many sort of similar looking types of problems, and you just got to keep it straight exactly what you're doing in each one. So that one, its value was -12. When I plug in -1 here, f of -1, plug that into this formula up here. I did this ahead of time. I got 16. And then plug in 3. And I got f of 3 is -8. So these you can do with a calculator if you're doing the homework. All right? And so what's my final answer? This is all there is to it in a problem like this. You choose the biggest and the smallest. So in this case, 16 is the maximum and -12 is the minimum. You're looking for the biggest number overall and the smallest number overall. All right, so my final answer is the absolute minimum is at x equals 2 and y equals -12, right? And the absolute maximum is at x equals -1 and y equals 16. That's all there is to it. Any thoughts about that? There's not a whole lot that can go wrong here. I got one more, and then I have one for you all to try. There's actually one little thing you gotta watch out for, which will occur in this example that I'm about to do. So let's just try another one here. How about, this is a slightly more complicated function. 3x to the 4 plus 8x cubed minus 18x squared on the interval -1 to 1. All right. We do the same stuff. So we are eventually going to make that chart. The chart must include all the critical numbers and the two interval endpoints. So we should find the critical numbers. That is, you take the derivative first of all. Someone want to shout out for me? What's the derivative going to be here?
12x cubed
Mm-hmm.
plus 24x squared minus 18. Minus 32.
36, I think. Excellent. Yes. You gotta do the derivative. No surprises there. This one is a little more interesting than before. We should try to factor this because we're gonna have to solve for x here. So I say I can factor out 12x from the whole thing. And then what remains is x squared and 2x and minus 3, like that. And then that thing can factor some more, and this will do it for us. So this is 12x. Can anybody say how do we factor the other part there? Anybody spend the holiday factoring with your family?
You can do x plus 3 and x minus 1.
X plus 3 and x minus 1. I agree. Excellent. I didn't do any factoring over the break, but I actually did use trigonometry in my real personal life yesterday. This almost never happens, but it's true. I had to, my kid got some, in my opinion, overpriced lip balm. It was like a Hailey Bieber, had a very fancy sounding name. I forget what it's called. Road with a H, Road. Anyone know what I'm talking about? Yeah, all right. She got this thing, and then she wanted as a present for her friend. And then we just got a 3D printer. She wanted to 3D print a cute little thing to put it in to give it to her friend. And are you interested in this story? I don't know. So we made this little thing with like a round opening in the top that you could stick this thing in it like that, and it would stand there, you know.
She's a good friend.
And the yeah, that sounds cute, I guess. And the we don't have the thing yet though. She ordered it, but it didn't come yet. And she has to give it to her friend today. So we made this thing. So she's gonna say, here's this thing that you can put it in once you get it, but I don't have it yet. And so we looked up. We want to know how big is the hole going to be that the thing sticks in, and the listing on Amazon tells you the package dimensions. This little thing is in a rectangular cardboard box, but we want to know the circumference of the cap. The cap of it is a circle, but it's inside of this rectangular box, so we had to figure out with some simple trigonometry. It was great. My kid might have been impressed with my skills, but we will find out. It might be the wrong size, in which case my kid will not be impressed with my skills. We'll see. We didn't get the thing yet. Anyway, that's my story for what I did last night. The critical numbers, right? This is what we were trying to do here. That's the derivative. We set the derivative equal to 0 and solve for x. So for the critical numbers, I go 12x, x plus 3, x minus 1 equals 0. Solve for x. I get 12x equals 0, x plus 3 equals 0, x minus 1 equals 0. This gives me x equals 0, x equals negative 3, x equals 1. So there are 3 critical numbers in this case. These numbers go on my little chart together with the interval endpoints. So my little chart here, x and f of x. Here I'm going to use my calculator to plug these numbers in. The numbers are 0, minus 3, 1, and the 2 endpoints, minus 1 and 1. And here I said something slightly interesting was going to happen. This is that time. The interval endpoints are minus 1 and 1. Now, one thing which is not terribly interesting, 1 appears on our chart twice. That's because it's just by coincidence, one of the interval endpoints is also one of the critical numbers. So you don't have to consider it twice, but whatever. This one I don't really care about because it's on there twice. The other more interesting thing is negative 3 right here. I am also not going to consider negative 3. Anybody see why in this case? You should not. You don't need to, and in fact, you should not. You'll get it wrong if you consider the value at negative 3. Yeah.
It's because x is 0. Like in the middle.
No, not necessarily.
The interval.
Yes, because negative 3 is outside of the interval. All right. We are only talking about the maximum and the minimum values in this interval, and negative 3 is not in the interval. It turns out actually, if you do this on your calculator and plug the values in, the negative 3 actually does give you the smallest y value, but it's outside of the interval, so it doesn't count for this problem. So this here is being excluded. Omit any points outside the interval. And if you don't do this, if you do include it, you might sort of falsely say that negative 3 is the minimum, right? Which, like, by y values it is, but we don't consider it because it's outside the interval. So that's just one very small thing that you need to pay attention to. But anyway, I'm going to plug the rest of them into the function, and I'll use my calculator. Actually, the first one is easy to do, in your head. This one, if you plug in x equals 0 up here, you get 0 as the answer. The others, 1 is not hard either. If I plug x equal 1 here, it says 3 plus 8 minus 18, which is -7. That's 1. -1 is similar, but the signs are messed up. When I did this, I got -23. All right. This one actually I think is totally fine to do without your calculator, because since you're just plugging in 1s and 0s. All right. Anyway, what's the maximum and the minimum? Here they're all negative or 0, so the maximum is the 0 and the minimum is the -23. The maximum is x equals 0 and the y value is 0. And the minimum is at x equals -1, the y equals -23. The most negative is the minimum. The least negative is the maximum. All right. Great. I got one for you all to try. Let's try. So I thought we'd do like a real world kind of a word problem here, just because we don't do a lot of those. Let's say my merch store. This is about my merch store. Of course, the profits at my merch store, they go up and down from day to day. Let's say that my merch store profits vary each day, like this here. P of T. P is for profit. I just made up this formula. This is not realistic. All right, let's say this is my formula. So this is the profit, dollar profit on day T. So if you plug in 1, that tells me how much profit I made on day 1. Plug in 2, that's how much profit I made on day 2, etc. And the question is, on which day is my profit maximized? And let's say which day from 0 to 10 has my maximum profit. And a little follow-up. What actually is that profit? All right. So this is a word problem in which I'm asking you for the maximum. You have to do all the same stuff, and you will end up finding the maximum and also the minimum at the same time, although the specific question I'm asking is only about the maximum. But you should do the same procedure. Actually, there's not a good way to only find the maximum without also finding the minimum. You're going to do both. All right, see what you think. You will probably want to use your calculator when it comes to plugging the numbers in. Otherwise, you can do everything by hand. is not.
Yeah.
That came from this part.
Yeah.
But if it had said 6x and there's a, and you divide 6 to solve for x is 1/6. There's no x here. So you don't get a. You get this. Unlike here, see that one had a. You choose to do this. This doesn't. So really.
So I don't include it at all.
That's what you're supposed to do. Well, in this case, you do because I said from 0 to so 0 is the left hand side here. You have to include the 2 endpoints, and one of them is 0, so you should actually be 0.
But then
It's
what
not.
is, but then what is this?
That gives you no solution.
Yeah, so I don't include it.
But you do pass now. Yeah. Like what you're listing here should be all of the endpoints, 2 endpoints, and also all of these numbers.
So I include negative 6.
No, because that's not a solution for x.
So I don't.
Yeah, this part.
All right, I think we can talk about this one. It looks like folks did fine. So I started it off here. That's the derivative. You should factor out negative 6, and you make this, and then you continue to factor. It should say t minus 2 and t plus 1. Those are the factors of that thing. And so when I set this equal to 0 and solve for t, I get t minus 2 equals 0, which means t equals 2, and also t plus 1 equals 0, which means t equals negative 1. All right? And I didn't say this explicitly, but what's the interval that I'm considering? It should be the interval from 0 to 10. All right? Because I said there, which day from 0 to 10. So the interval is the closed interval 0 to 10. All right? So when I make this little chart of the x and y values, I suppose they're actually t, but whatever, and p of t. The things that I put are the critical numbers, which are 2 and negative 1, and the interval endpoints, which are 0 and 10. Because negative 1 is outside the interval, I do not consider negative 1. All right? That's because this is outside the interval. So you should not plug in negative 1. If you do consider it, you might sort of get a false maximum, which is not actually legal in this problem. Anyway, I'm going to plug these numbers in with my calculator. So plugging in 2, I got 19. Plugging in 0, I got negative 1. And plugging in 10, I got this somewhat ridiculous number. I hope this didn't throw you. Anybody agree with those numbers? This is what I got when I plugged it in on my calculator. That silly number there is because this is a made-up equation. Actually, little known fact, I actually do have a merch store, because once I made this thing which doesn't, I found an old thing like from the 1800s, a poster, and I remade it, and you can buy it. My profits are 0, like almost every day. Every so often somebody buys something, and then my profits skyrocket to like $3 or something. Anyway, what's my answer then? Okay, the question, which day has the maximum profit? The answer is day 2. That's this one, right? That's the maximum. I suppose this means if the formulas are valid, it means that on day 10 I lost $1,500 somehow on my merch store. I never go below 0. It's just 0. All right, so this is the maximum. So to specifically answer the question that was asked, the maximum profit is on day 2. And then the parenthetical question, what is that profit? It is $19. Right? I hope that's what you said. Any questions about that? That's how it goes. All right. I see we have about 20 minutes remaining, and I think that's enough time to discuss antiderivatives. Can we switch gears like permanently? So the rest of the course is actually not about the derivative anymore. It's about the antiderivative, which still has the word derivative in it, but it's something else. Antiderivative. This is what we're going to focus on for the rest of the semester. Antiderivatives, as the name suggests, is about doing the derivative backwards. So for now, I will present this as just sort of a cute thing that you could do if you want to, although there are good reasons to do the derivative backwards in real life, and we'll see eventually. But for now, I just want to talk about doing the derivative backwards. For example, this is trying to answer questions like 3x squared is the derivative of, anybody say? This is like if I tell you the derivative and I'm asking you to tell me what's the original function that this one came from by taking the derivative. What do you say? X cubed, yeah. Once he said it, I hope that everybody agrees. Yeah, actually that is the derivative of x cubed, all right? So this process where I tell you the derivative and I ask you for the original function, that's called the antiderivative. If you start with something which you imagine is the derivative, and then you go backwards and find the original function. That's called the antiderivative. All right, 3x squared is the derivative of x cubed. Generally speaking, the antiderivative is harder to do than the ordinary derivative. One reason why is actually that's not the only answer. Can anybody think of another function whose derivative is also that? There's actually more than one. Yeah?
Would it be like x cubed plus a constant?
Yeah, how about, or x cubed plus 1, right? The derivative of that also, because the 1 will go away if you take the derivative, the derivative of that also is 3x squared. Or, it doesn't matter, I wrote plus 1, but he said plus a constant. It doesn't matter what you put there, right? Any constant term there will disappear when the derivative is taken. And you're going to get 3x squared. So actually, it's anything like x cubed plus c. And this is how we're usually going to write it. Plus c. When you're doing antiderivatives, basically every answer is going to have an extra plus c on it, which is just something you have to remember. It's almost never important, but you have to remember to put that plus c. All right? So the process, 3x squared becomes x cubed plus c. All right? This is called the antiderivative. It's certainly not the same as the derivative, but I mean, it's obviously related to the derivative. It's just doing the derivative, but backwards somehow. All right? And we say, so the antiderivative, if you wanted to say this in words, the antiderivative of 3x squared is x cubed plus c. All right? And the way, of course, we're not usually going to write that out in words. There is a special kind of symbol for this. Remember, this, d over dx, f of x, this means the derivative. There is a similar sort of symbology for writing the antiderivative, and it looks considerably more exotic, and you can impress your friends by writing things using the antiderivative. It's this. This is called the integral sign, that thing which looks kind of like an S, but it's tall and skinny, like me. I'm less skinny than I once was, but just as tall. That's called the integral sign. It's meant to look like an S for reasons which we will talk about eventually. And, this is weird, you put a little dx over there, all right? That means, so the first one up there, that means the derivative of f of x. This one means antiderivative of f of x, all right? you may ask yourself, what is this dx supposed to mean? And this is a somewhat unsatisfying answer, but we write this sort of for historical reasons. I mean, people started writing it like this back in the days of Isaac Newton. But the dx here is meant to represent something like this dx here. And what I would have said earlier on, if you had asked me, what exactly does dx mean here? I would say it doesn't actually mean anything, and this thing, d over dx, is not really a fraction. It's just meant to somehow be reminiscent of some kind of a rise over run formula, because this is supposed to represent the slope of something. And if you imagine the derivative is somehow like dividing by dx, the opposite of that, or the reverse of that, would somehow be like multiplying by dx, and that's why we put this dx here. It doesn't actually mean anything by itself. It just indicates that I'm doing the antiderivative. So the integral sign, which is what this is called, and the dx together, they mean the antiderivative. It's a little weird. It almost never is worth thinking about. You just write the dx when you're doing the antiderivative of something. And of course you write the integral sign. All right? Okay, anyway, let's just try some examples. So for example, integral of 3x, I meant to say this thing here, the antiderivative is also called, I've already said this a few times, the indefinite integral. Or I will just say the integral. There is also something called the definite integral, which we will get to later on in a couple weeks, but for now we're going to stick with the indefinite integral. All right? And so when I see this, if you ask a typical person on the street, what does that mean? They'll say, that's the integral. You can say, isn't it the antiderivative? And they'll say, yeah, well, yeah, that's the same thing, the integral and the antiderivative. All right, so antiderivative is also called the integral. Anyway, some simple examples here. The integral of 3x squared dx. You always put that dx there. It doesn't actually really mean anything. It's just part of how we write the antiderivative, or the indefinite integral. Anyway, we said before, this is x cubed plus c. All right? And we are going to learn all kinds of rules for doing the antiderivative, rules for the integral, just like our rules for the derivative. And they are mostly similar, although sometimes different. So, you know, that's sort of where we're headed for the next couple weeks. How about 2x? Anybody, at this point, we don't know the rules yet, so we're just sort of guessing. Can anybody guess? I am thinking of a function to go here, so that the derivative of that is 2x.
X squared.
X squared. Plus c, yes, thank you for remembering the plus c. Because this is called the integral, this plus c is often referred to as the integration constant. And like I said, it usually doesn't really matter. That's a mic drop. Answer the question and then walk out. The integration constant is the plus c, all right? You have to remember to put the plus c. It's technically not correct if you don't put the plus c, but it usually doesn't really matter for anything. All right, how about this? What if it was just x? This one's a little harder. Any thoughts about that? Can you imagine a function so that when you take the derivative, you got just x, not 2x? 1x? I don't think that would work. Where this 2 came from is because when you have x squared, you bring the 2 down, you get 2x to the 1. Could I do something somehow, perhaps? I'm thinking somehow, could we, I want to make something like this, but somehow compensate for the fact that there's going to be a 2, but make it cancel out, so you just end up with a 1x. Yeah? 1/2x. Did she say 1/2 x squared? Plus c, of course. 1/2 x squared. Yeah, I hope you see. I mean, these ones, once you see it, it's fairly easy to realize that this is the correct answer, because if you took the derivative here, the 2 would come down, multiply times the 1/2, and it would give you 1. basically cancels the 1/2, and you end up with just x, which is what I want to see over here. Yeah, so there are, maybe this looks exotic, but this is actually a simple example once you know the appropriate kind of tricks to do. How about this? What if it was just a number in there? Everybody knows the derivative of a constant is 0. What about the integral of a constant, the antiderivative? 4x. Yeah, this is what you need over here. 4x plus c, of course. This is what you need so that when you take the derivative, you just get 4. All right, so this is actually a rule for if you have the integral of a constant, the answer is always that same constant times x. That's how it goes. All right. And I will just say, we can always check the answers by doing the derivative. So if these are, like if those were test questions, you could always check your answers by doing the derivative. Like for example, if I said integral of 2x dx equals 1/2 x squared plus c, to check it, I would do derivative of 1/2 x squared plus c and see what I get. And the answer is I would do this 2 and the 1/2. The 2 would come down and multiply the 1/2 and then give me x to the 1 and then plus 0, which is x. What? Sorry, I shouldn't have wrote the 1/2. I mixed up my 2 examples. Take the 1/2 out. Sorry about that. It's like this, 2x, right? And this checks out because this 2x equals that thing on the inside. All right. If you have an antiderivative, you can check your answer. By taking the derivative of the answer you got and making sure that it equals the thing that you started with. All right. Okay, there's sort of a typical rule to use for powers of x like this. Can we try and explain this? Remember the derivative rule for a power, the power rule, which everybody knows by now because we do this so often. The derivative of x to the power n equals nx to the n minus 1, right? This is the thing that everybody knows where you bring the power down to the front and then you decrease the power by 1. How can we do this backwards? I just want to think about reversing the process. So this I would describe, if I were to describe in words here, you multiply the exponent into the coefficient, right? That's what if I were to say technically what happens here, this n, which used to be an exponent, is multiplied into the front as a coefficient. And then you decrease the exponent by 1. So multiply the exponent into the coefficient and then decrease the exponent by 1, right? This is the procedure for taking the derivative. Can we do this in reverse? Flip it and reverse it, as she says. How do we do this backwards? You just do the opposite of those 2 steps, and you have to do them in the opposite order also. This is like if you're trying to reverse a procedure, like if I put on my socks first and then put on my shoes. To reverse the process, you have to do it in the other order. You take off your shoes first and then take off your socks, right? This is a little life hack. Anyway, to reverse this procedure, the last thing I did was decrease the exponent by 1. So the opposite would be increase the exponent by 1. And then the other thing, it said multiply the exponent into the coefficient. To do this in reverse, I should divide the exponent into the coefficient. So then divide the exponent into the coefficient. All right, so what that looks like, if I write this out as a formula, it is you increase the power by 1. Instead on the derivative you decreased it, but here you increase the power by 1 first, and then you divide by the new power, which is most convenient to write this way. And then you say plus c. increase the power, that's why it turns into n plus 1. And then you divide by the new power, which is the same as multiplying 1 over n plus 1. All right? This is the power rule. So this, you should definitely memorize this, although like the power rule, it's something you're going to do constantly, and so you don't have to work too hard to memorize this, but this is the power rule for the antiderivative. It plays the same role as the power rule for the derivative. Like it's just as important, and you're going to do it all the time, so you definitely need to know how to do it. So for example, you know, we've already done this, but x squared dx, the integral will be, I increase the power by 1, so it turns into x cubed, and then I divide by 3 in the front, which is the same as multiplying by 1/3, like that, right? This is a typical antiderivative of a power of x, all right? You can do this even for negative powers if you want to. If I had something like 10 x to the minus 10 dx, can somebody say what would that look like? You increase the power and then divide by the new power. I'll give you a hint. It ends with plus c. That's not a helpful hint. Increase the power by 1. Can anybody say what's the new power going to be? You increase by 1. Negative 9, yeah. It used to be negative 10. You add 1, it becomes negative 9. And then you go 1 over the new power. So it's 1 over minus 9, like that. This is what it looks like. All right? This works for any n. Right? It can, that n up there that you see at the top, it can be positive or negative, whatever. It can be 1/2, that would be like a square root, right? You can still do the same rule. It works for any n, except there is one exception, except n equals negative 1. That's because if you try n equals negative 1, it looks like integral x to the minus 1 would become, I add 1 to the exponent, it would become 0, and then divide by 0, and that's the issue. This dividing by 0 is bogus. You're not allowed to divide by 0, as everybody knows. And so actually, there's a special rule. You should not even try any of that. There's a special rule that you have to use for the special case of a negative 1 power, but we will get to that not in the next 5 minutes. So I will just say, beware. There's a special rule for the minus 1 power. Don't try this if it's a minus 1 power. You will get 1 over 0, which is a nonsensical answer. All right? I got just a couple more things to say, and then we can do some more complicated examples. So one thing that everybody knows about the derivative is if you have a bunch of stuff added together, then you can just do the derivative of each of the things and add together all the answers. And the same is true for the antiderivatives. So antiderivatives are easy for sums and constant multiples. Exactly like the derivative, and it's for the same reason. If you have antiderivative of things added together, you can just separately do each of the things added together. What I mean, to write that like a formula, what I mean is this. If you have two things inside the integral sign, this is the same as doing the first one and then also doing the second one. There's no special business you have to do if they are added together. If they are multiplied, you better believe there is special business. Just like for the derivative, if they're multiplied, you have to do the product rule. For the integral, if they're multiplied, there's another special thing that you have to do. So we're not going to talk about that for now. Sums and constant multiples. This is also true if you have multiplication by a constant. It's just like for the derivative, multiplication by a constant, you can sort of ignore the constant and just leave it as a constant in front of the answer. And the same is true for the antiderivative. How I would write that is like this. K integral f of x dx. This is a fancy way of writing what I just said in words. If you have a constant multiple, you just write the constant in front of whatever the antiderivative of the rest of the thing is. All right. So, for example, I can do something like the integral of x squared plus 4x plus 5 dx. First of all, because these are things added together, it means I can just do each one separately. So they are added together. So just do each separately. That means my answer, I can just start writing the answer immediately. What happens to x squared? You do the power rule. The squared increases by 1 and becomes x cubed, and then I divide by the 3. So the x squared becomes, maybe it's clearer if I write it sort of this way, like this. Right, x squared turns into that. What about 4x? So then plus, of course, 4x. Okay, I know how to handle just x. You think of x as being x to the 1. And then you can do that thing with the power. What about the 4, though? What do you do with the 4? It's what I just said. The 4 being a constant multiple just stays in front as a constant multiple. So I just leave the 4 times whatever happens to the x. And the x becomes 1/2 x squared. That is, you increase the exponent by 1. You divide by the new exponent, which is 2 now. And then the last one, 5, becomes, anybody remember this? This is a special rule about just a constant turns into 5x. Yeah, if you have just a constant, it always becomes that same constant times x. And then, of course, I put the plus c at the end. All right, this is how we do it. Much more on that next time. I think that'll do it for now.